Hello everyone, I will be summarizing the chapter on RF mixers. In this presentation, I will be explaining what RF mixers are, why we need them, and how the mixing process is done. We will then discuss conversion loss and isolation. We will then talk about what frequency inversion is, and finally in the end we will discuss the other mixer products. Yalla, let's begin. Okay, unlike amplifiers that make signals larger, a mixer shifts a signal from one center frequency to another. Mixers are useful components in both the transmitter and in the receiver. And this is because on the receiver, it allows you to take the high frequency antenna signal and down convert it into a signal where it is easy to do operations on, such as filtering and data conversion. And on the transmitter side, it allows you to do the data conversion and other operations also at low frequencies, and only very late in the transmitter chain up convert your signal to a high frequency where it can be amplified and transmitted. And again, why are we doing this shifting in frequencies? Well, for several reasons. The number one reason why we shift frequencies is because the frequency of the signals our wireless transceiver will receive or need to transmit is already chosen to us, is already set to us based on several standards such as Wi-Fi's 2.4 GHz, for example. And these standard frequencies have nothing to do with the requirements of the filters, demodulators, and so on that we will have to design or choose. So, for example, here in the receiver chain, we will have to filter the incoming signal before passing it to the digital to analog converter and DSP and so on. And if we want that filter to be narrowband, it is easier to build it using low frequencies as opposed to high frequencies. So that was filtering. We may also need to shift the frequency to work with available components, as we said, and shifting frequencies allows us to use different antenna sizes and still be able to use the same components that work on their optimal frequency range. We know from the previous chapter that if we have a nonlinear device, say a nonlinear amplifier here, it will produce at the output frequencies that were not present at the input. So if we pump into that nonlinear device a signal omega-1 plus omega-2, then at the output all these intermodulation and harmonic frequencies will appear, including omega-2 minus omega-1 and omega-2 plus omega-1. So we wanted to amplify our signal here, but if we look at the second order terms, what also happened was that we shifted omega-2 by plus omega-1 and minus omega-1. So did we just create a mixer? Well, almost any circuit you design will be nonlinear to a certain extent. And maybe that's nice because this means that in practice, you cannot fail in making a mixer. Any circuit you design will be nonlinear, and any nonlinear circuit will mix signals together. And this is fundamentally different from how we design amplifiers, because it is very well possible to design an amplifier circuit that does not amplify a signal properly. So, are we done? No, there are several problems here. Notice that the output contains all these frequencies that we don't want to mix. Also, the output signals at omega-1 and omega-2 are larger than the frequencies omega-1 plus or minus omega-2, which we want. So the question now becomes, how do we build a good mixer? Regardless of the circuit implementation, what we want from the mixer is to ideally perform multiplication in the time domain, and therefore if this is our input signal, then the output is the sum and the difference as shown also here on the frequency spectrum. Now, it is important to understand from the beginning that all our analysis in the next few slides is based on the assumption that we have an ideal mixer which produces only two frequencies at the output. Here I am showing the block diagram of a mixer in a typical scenario where it is used to convert an RF signal to an IF signal, an intermediate frequency signal, using a third signal called the local oscillator. So, based on our previous discussion in the previous slide, the output frequency FIF is equal to FLO plus or minus FRF. Now, to make sure that the mixer does not produce many signals that we don't want, the local oscillator power level is usually at least 20 dBs higher than the RF signal. And this is what I'm showing here. Now, this diagram is showing the process graphically. So, the signal is coming down from the antenna and it contains all these frequencies. But the frequency we want is located at FRF. Now the problem is that at very high frequencies, it is very hard to create a very narrow bandpass filter. This is why we try to filter as much as possible at RF, and then what we do is down convert our signal using the mixer to a lower frequency FIF, and then use another bandpass filter at a lower frequency to filter only the signal we want. And this also has another advantage, because now whatever the RF frequency we want, we can bring it down to the same IF frequency, and all the components following the IF filter have to work at only the IF frequency. Now during the conversion from RF to IF, some of the power is lost due to the mixer. This is why we define something called the lower sideband conversion loss, which is the difference in power level at RF and at the difference frequency at the output. And similarly, we can define the upper sideband conversion loss. So, for example, if we have the conversion loss from a datasheet, and if we know the input power at RF, we can calculate the power level at the sum and at the difference frequencies at the output. Another thing we need to consider is leakage between the mixer ports. So, for example, if we apply a local oscillator signal at the LO port, some of this signal will leak and appear as FLO at both the IF and RF ports, and without any frequency translation. This is important because we will have an antenna here, and we don't want the high power LO signal to radiate through the antenna and interfere with other receivers. In fact, one of the jobs of the RF filters right here is to attenuate any LO signal leaving out of the RF port. Another problem is that we might have another mixer connected to our first mixer. And we don't want any of the LO signal to pass through the RF port of the second mixer. In fact, this is one of the jobs of the IF filter right here, to attenuate any LO signal leaving out of the IF port. So we can characterize a mixer by the isolation between each of its ports. We have the RF LO, we have the RF IF isolation, and the LO IF isolation. And here I am showing the LO RF isolation because it is the one we care most about. And the other two can be calculated in a similar way. We have previously identified this important equation that allows us to find the frequencies at the output of the mixer. And due to the plus minus sign right here, there will always be two solutions anytime we solve for one of the variables. So we will have two solutions when solving for FIF, two solutions when solving for FRF, and two solutions when solving for FLO. Now, where did this absolute value come from? Notice that if FRF is less than FLO, which is called the high side LO, high side local oscillator, then the mixer output at the difference will always be positive and above 0 Hz. However, if FRF is larger than FLO, which is called the low side LO, then the output frequency will be negative or below 0 Hz at the difference. So what does a negative frequency mean? We should remember that we started with the cosinusoidal RF input and that cosine of minus omega t is equal to cosine omega t. And this means that any mathematically negative frequency is practically the same as its positive value and hence the absolute value. So let us now consider this example here where we have an RF signal with a band from 3.7 to 4.2 GHz with a center frequency of 3.95, and we want to down-convert that into an IF band between 0.95 and 1.45 GHz with a center frequency of 1.2 GHz. So the question is, what should be the local oscillator signal frequency to achieve this conversion? Plugging into the previous equation, we already know that we will get two local oscillator frequencies, and here they are, the low side local oscillator frequency and the high side local oscillator frequency. Now a question that naturally arises is, if both will convert our signal to the desired IF, is there really a difference between using one LO frequency over the other? The answer to that is yes, there is a difference, and it has to do with frequency inversion. But let's see what that means. So, if we use an LO frequency of 2750, which is the low side LO, we notice that the lower band edge, right here, will shift to 950, and the upper band edge will shift to 1450. Okay, that's great. Now let's see what happens if we use 5.15 GHz as our LO frequency. 3700 will shift to 3700 minus 5150, which in absolute value will give 1450, and 4200 will shift to 4200 minus 5150, which will give 950. Something interesting happened here. Our RF spectrum got inverted or flipped around. So is this a problem we have to worry about? Well, although frequency inversion does not change the information content of the signal, it changes how we interpret the signal in the demodulation stage later. So, although frequency inversion is not problematic, we need to know when it occurs to be able to interpret the signal properly. What we will do now is try to formalize frequency inversion, but in order to do that, we will need to introduce some terminology. So, if we have an RF signal band, it will have two edges, a lower band edge and an upper band edge. For each edge, we will have two possible LO solutions. Either we choose the LO to be lower than the RF frequency, and this is the low side LO signal, which is here and here, or we choose the LO to be higher than the RF frequency, and this is the high side LO signal, which is here and here. Now we know that FLO is FRF plus or minus FIF, and this is exactly what I'm showing in these four relations. The minus sign will give us the LSLO, and the plus sign will give us the HSLO. Okay, so now I'm an RF engineer. I know that I can use two local oscillator frequencies, and the question is, which should I choose? Let's first consider that we use the LSLO, which means that FLO is less than FRF. Now, based on this relation that we derived earlier, the plus sign will give me this band on the right, this spectrum on the IF, and the minus sign will give me this IF band, which is below 0 Hertz or negative. But we know that in reality we can take the absolute value, and what this will do is re-invert the spectrum. So the lower sideband and the upper sideband are not inverted. Now let's consider that we use the high side local oscillator frequency, which means that FLO is larger than FRF. And if we use this relation that we derived earlier, using the minus sign, we will get the lower sideband, and using the plus sign, we will get the upper sideband. And we notice that since we're using HSLO, both of them will be above 0 Hertz or positive. And this means that the lower sideband is in fact really inverted, and it stays inverted. And this is exactly what we saw in the example when we took the high side local oscillator frequency and only showed the lower sideband. So to conclude, frequency inversion occurs when using HSLO and selecting the lower sideband only. Okay, now we will look at the same problem we had, but from a different perspective. In the previous example, we were trying to solve for the LO frequency. Here, we removed the RF bandpass filter, so we're trying to solve for the RF frequencies that satisfy this LO frequency and this IF frequency. And solving for FRF, we know that we will get two frequencies as shown here. Now, without the RF bandpass filter, this is a problem. If we assume that the signal we want to downconvert is 3.95 gigahertz, then that's great. That's what the mixer is doing. But the mixer is also downconverting any signal at 1.55 gigahertz, and this signal will now appear at the IF port as noise that we don't want. And here I'm showing it graphically. This is the signal we want to downconvert at 3.95 gigahertz, and this is the image frequency at 1.55. Without any RF bandpass filter, this image frequency passes to the mixer output and then through the IF filter. And this is exactly another reason why the RF bandpass filter is important. Another concept we can mention here is the image response rejection ratio, IR, which is the ability of a receiver to reject the image frequencies. And this is used to characterize the performance of heterodyne transceivers. Okay, now we will derive some relations for the image frequencies. So we previously already derived these equations when solving for the LO. These two are when we're solving for the LSLO, and these two if we're solving for the HSLO. So if we are going to solve for the image frequencies, we will also have four relations, two with the LSLO and two with the HSLO. So for example, this one right here is the low side image frequency at the lower band edge. And this one here, for example, is the image frequency, is the high side image frequency for the upper band edge. And based on these two relations, we can deduce a relation for the range of the LSLO image frequencies. And similarly, based on these two, we can deduce a relation for the range of the HSLO image frequencies. Piece of cake. In all our previous discussions, we were assuming that we had an ideal mixer. So we were considering that we only had second order terms at our output, in fact. But we should remember that a mixer is a nonlinear device. And this means that this, in fact, is the output spectrum of frequencies that we will have at the IF port, We will have all the RF frequencies and all the harmonics. We will have FLO and all its harmonics, as well as all the different intermodulation products. And this is what I'm showing here. We're already familiar with this spectrum. Now, the question is, how do we know the power level of these so-called spurious signals? And the answer is that they're given in any mixer's datasheet. So here I found a mixer from Analog Devices, and this is the datasheet. It is based on a doubly balanced mixer topology, which is in fact the most common mixer topology used. Notice here that like any nonlinear device, it has a third order intercept point and a 1 dB compression point. And here I'm showing the mixer with the RF input port, the LO port, and the IF port. So the datasheet had several tables, and one of them was this one right here. They're telling me the power level of the LO signal as well as the frequency of the LO, and the power level of the RF signal as well as its frequency. And both of these are fixed. And what they're showing me in this table is all the different combinations of N and M, which means all the different intermodulation products. And the numbers here in the table, all these numbers, they represent the relative level in dBs that a particular IM product is below the power level of the desired product, which is FLO plus or minus FRF. So our desired frequency has M equal to 1 and N equal to 1, and this explains why we have 0 dBs right here. By looking at the numbers in the table, we can generalize a bit and say that even by even products and high order products produce or have a low power level, and thus they are the least to worry about, while odd by odd products and low order products are very close in power to our desired signal, and thus they cause the most trouble to our mixer. We can also say that the power level of the spurious signals or spurious products are a strong function of the input power of the RF signal and the input power of the LO signal, as well as the topology of the circuit. But these spurious signals are a weak function of frequency. This is why we care more about here the input power level of LO and RF. Okay, let's say now that we are given a certain RF band and that we are using these LO frequencies and that we have a band pass filter at the IF with a 45 megahertz center frequency and a 1 megahertz bandwidth. And the question is, can we know if a certain spurious product will lie inside our bandpass filter? This is the bandpass filter. And the answer is yes, of course. By simple manipulation of this relation that we derived earlier, we will get two relations for the lower sideband output and two relations for the upper sideband output. This is the lower sideband output. It has a lower edge and an upper edge. And this is the upper sideband output. It also has a lower edge and an upper edge. Lower edge and an upper edge. So in this example, they want to know if the 2x3 spur will lie inside the IF bandpass filter. And by doing the calculations, we find that, in fact, these are the two bands at the output for the 2x3 spurs, and none of them lie inside our IF bandpass filter right here. So everything is fine and we're all happy. And that's it. Lovely, lovely, lovely concept.